And we are recording now. Welcome to unit one of these things, anatomy. Unit 4, I believe it is. We are looking at the inner ear, anatomy of the inner ear, focusing on that in particular. Actually, this is unit 5, inner ear anatomy. And we got to the bottom of page 2 in our notes last week. We covered basically the vestibular system. We talked about the membranous labyrinth, the bony labyrinth. We talked about the fluids that are inside each of these labyrinths. Very important to realize that both vestibular system and cochlea share perilymph. They share endolymph. They both have hair cells. They have efferent hair cells and afferent hair cells. So in those ways, they're similar. We went over the sense of balance, talking about the 3 portions that give rise to the sense of balance: vision, proprioception, and the vestibular system. We then said the vestibular system itself has 3 parts: the macula, the saccule, or I should say the utricle, saccule, and semicircular canals. We gave the acronyms BPV and ENG. Keep these close to your heart. Then we went into the inner ear and the cochlea, and we described some of the gross anatomy, working our way down to about the bottom of page 2 in our notes. So let's just share screen now and get to where we are. Good old notes, here you have it. This is very important, this section here, realizing what they all have in common, the basic pieces and parts therein. The vestibular system goes down to the bottom of page 1 and up to the top of page 2. And then at the top of page 2, we began our coverage of the cochlea. It has 2.5 turns. Don't worry about memorizing how wide and how tall. Just think of it as basically the size of the tip of your pinky finger. Remember, too, that the cochlea is remarkably inaccessible, buried in the hardest bone of the body, which is the petrous portion of the temporal bone. Petrous portion, which surrounds part of the middle ear space and, of course, all of the inner ear. Think of the cochlea as like an auger-twisted hole into the bone. Note the location of the bony and membranous labyrinths. So, looking here at the bony labyrinths, remember everything white on this slide is solid bone. And the bony labyrinth is right here at the outside. Think of that as a hole dug into the bone filled with perilymph fluid, P-E-R-I. And then we snuck or slid a hose inside that tunnel that we dug in the bone, and that hose is called the membranous labyrinth, and it is filled with endolymph. Now, endo always means internal, so what's always the inside fluid? Peri means outside, perimeter of a square. Okay, the perimeter of your lawn. It's the outer stuff. So endo inside, peri outside. So looking at the membranous labyrinth, here it looks a lot like a round hose. When we go to the next slide, here it shows it again. Okay, looking much like a round hose. This black snake here. But if you look closer, you can see that that's actually a bit triangular shaped. And then when you're looking at that triangular shape to it, that 3D triangular shape, looking even closer, you can see how that shape serves to divide the bony labyrinths of the cochlea into 2 halves. And that's what's most important to grip and to grasp. The 2 halves. This is a picture only of the membranous labyrinths, of the vestibular system on the left and the cochlea on the right. And you can see all, whoops, don't move that, Ted. And you can see all the fibers of the 8th nerve from the vestibular system and the cochlea migrating together to go to the brain. Here now is a cross-section of a cat's cochlea, and note well the orientation of these things. Okay, here you go. Here's the bottom coil, the middle coil, and the top coil. And note how the bony labyrinth, right where I'm circling here, and bony labyrinth here, and membranous labyrinth at the triangular shapes. Same here. Membranous labyrinth, membranous labyrinth, membranous labyrinth. Notice how the membranous labyrinth gets wider as you go toward the narrow apex of the cochlea. And you can look at the letters here. RM, Reissner's membrane. SV, stria vascularis, the blood supply, that little blackened area right here. Same with here. Okay? And you've got the, I think, spiral ligament here, SL. So you have scala vestibuli, scala media, scala tympani. Okay, again, bony labyrinth, scala tympani, bony labyrinth, scala vestibuli, membranous labyrinth, scala media. Oh, and the whole middle coil, this whole darkened area here, modiolus. The modiolus, the bony core of the cochlea. Here's my picture then of an unrolled cochlea to help give you some idea as to the arrangement this way. Oval window pushing in and out communicates with the scala vestibuli, bony labyrinth, pushing the fluid around the helicotrema, and then around out to the scala tympani, which is also bony labyrinth, bulging the round window out. As this pushes in, round bulges out. Scala media is the yellow in between. That's the membranous labyrinth, and that houses all the hair cells of the cochlea. They are inside here. There's no organs inside the bony labyrinths at all. Nothing but perilymph. The scala media is where it's at. Here's a picture of my picture of the cochlea. In other words, look at this picture and compare it to this picture. Same thing, okay? Only showing it more highlighted in color. And again, showing you the bony labyrinth, membranous labyrinth. And notice how the membranous labyrinth gets larger and larger as you move toward the apex. More and more mass, less and less stiff. More and more mass, less and less stiff here. And remember the orientation of the hair cells. You will have one row of inner hair cells all along the scala media, just like I'm drawing with my cursor here. And then you will have, and I'll bring it even larger so you can see it more, okay? Remember then, if I were you, I would take this drawing and I would say you have 5 rows of outer hair cells here, 4 rows of outer hair cells here, and 3 rows of outer hair cells at the base of the cochlea. Think of the wide end of the cochlea as the base, the narrow end of the cochlea as the apex. Wide end is the base, narrow end is the apex. And look at this picture to give you a better awareness. Look right where my cursor is. Inner hair cells and 3 rows of outer. Inner hair cells and 4 rows of outer. Inner hair cells and 5 rows of outer. Okay? And now looking at the movements of fluid through this stuff, stirrup or stay-piece pushing in and out of the oval window, scala vestibuli, bony labyrinth, follow the arrow, around, around and down through the helicotrema, out the scala tympani, out the scala tympani, out to hit the round window. Cross section, once again, the modiolus is in the center. Notice how this is an erroneous picture showing you as if the scala media gets smaller and smaller as you go to the tip, which is patently false. Notice the spiral ganglia, the cell bodies of the 8th nerve as they leave the scala media. Please remember you don't have 5 like shown in this picture. This is showing you 5 simply because it's a cross section. Much as my picture over here is showing you 5 or 6. But of course they're going all the way around. So I guess that's the thing I need you to know. So when we're looking now at one coil, a close-up of the coil, and make it our own business to really have this gross anatomy down, okay? Scala vestibuli, perilymph, Reissner's membrane, scala media, endolymph. And now the pieces of how this is held together. Spiral ligament on the right, holding the basilar membrane on this end, and the basilar membrane is the floor upon which the hair cells stand. And then you'll have spiral lamina on the left where my cursor is now, and that's holding the basilar membrane tight from this end. So the basilar membrane separates scala media from scala tympani. Reissner's membrane separates scala media from scala vestibuli. This bleb of fatty tissue here, tectorial membrane, inner hair cells, 3 rows of outer hair cells, so this must be at the base of the cochlea, and then all these supporting cells. And lastly, or not second lastly, stria vascularis, where my cursor is circling here, stria vascularis, the blood supply and oxygen supply to the cochlea, and your spiral ganglia on the left. So remember the 3 spirals: spiral ganglia, spiral ligament, spiral lamina, and spiral ligament. That's good. I always say there's 3 spirals. Bringing it closer, looking closer now. Spiral ligament on the far right, stria vascularis hugging the spiral ligament, blood supply, supporting cells, outer hair cells, inner hair cells, tectorial membrane, and then spiral lamina. Notice the 2 layers here, and what goes through those 2 layers of bone? Fibers from the 8th nerve. Fibers from the 8th nerve. Here's the cell bodies of the 8th nerve, the little eyes, and then that would actually close back together, as you can see here, and send the information up the 8th nerve to the brain. So basically, looking carefully now at this picture, you can see that there are spaces between the hair cells. Look at the areas between the hair cells. There are spaces here. And I will now, share the notes. So here we are. We're following this tightly, very close together. Bony labyrinth, high in potassium, low in sodium. Membranous labyrinth, endolymph, high in potassium, low in sodium. Ductus reunion, communication of endolymph between vestibular system and cochlea. Don't worry so much about that one. Here's your 3 scala. Okay, scala, scala, scala. All right, scala vestibuli, scala tympani, scala media. Helicotrema is the linkage between the scala vestibuli and scala tympani. And then here now we're looking at a close-up of the single turn of the cochlea, all of this written down. Reissner's, basilar membrane, spiral ligament, stria vascularis, modiolus, spiral lamina. Going to the top of page 3, spiral ganglion. Okay, we get a close-up of the scala media right here. So let's take a real close-up of it. And I said last week too, the whole scala media, the thing inside the scala media, all the cells together, is called the organ of Corti. So let's look at the organ of Corti right here. All of this in here, organ of Corti. Supporting cells, hair cells, basilar membrane, tectorial membrane. Really, all these parts comprise the organ of Corti. So if we bring the organ of Corti now closer, now you can see it very close. And again, notice the spaces surrounding the hair cells. Now those walls, look at the cell body walls, right where my cursor is tracing here. Okay, the fluid inside this area is kept separate from the fluid here. What kind of fluid is in the scala media? Endolymph. So look for endolymph circles. Watch my cursor. I'm going to bring it around. I'll make the picture a little bit bigger. Endolymph all here and inside of here, right where my arrow is going. Endolymph, endolymph, endolymph. Follow my little arrow. Endolymph, 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 and endolymph. Okay? But what is surrounding the walls of the hair cells themselves, right where my cursor is here, cortilymph. And cortilymph is perilymph inside the scala media. It's kind of like West Berlin was inside of East Germany, if you can almost imagine that, okay? Think of it as an island of perilymph inside the scala media. And why do you need to have that? Well, how are you going to get an electrical charge from just one kind of fluid? Batteries need different chemicals in them. And you need that interaction of endolymph and perilymph to create a charge, okay? Because what does the cochlea do? It changes things into electricity. It's one of the transductions. So if we bring this closer now, and we go to the next slide, look at the hairs of the inner hair cells. They will be bathed in endolymph. See? All endolymph in here. Whereas, see how they're pilloried? They're literally cut off at the necks. So the hairs, my head, is not in communication with my shoulders or body. So the hair cells are pilloried mechanoreceptors. Really, that's what they are. And so the walls of the cell body are in contact with perilymph-like fluid called cortilymph, whereas the hairs are in contact with endolymph. And I think that's the most important part of this particular part of the page, seen in the middle of page 3, right here, right where I'm highlighting. Make sure you know that. Now, do not worry about supporting cells, cells of Held, cells of Henson, cells of Claudius, space of Newell, inner sulcus, couldn't care less, doesn't matter, okay? But put a star by tectorial membrane, you got to know that one, okay? Make sure you have this too. Basilar membrane is narrower, less mass, more stiff at the wide base of the cochlea, and exactly the opposite. You know, it's wider, has more mass, and is more flaccid at the narrow apex of the cochlea. Those are the important things. Now let's really get close. Let's look at at the hair cells themselves as we move in closer. See this picture here? It's in cahoots with this picture here. This picture is showing you all the supporting cells, whereas this picture is showing you concentrating on the hair cells. So these two pictures complement each other. That's, I guess, what I want you to know. Now here's another picture of the organ of Corti, more shown in 3D. Instead of just a flat cut like this, you're looking a little bit more in 3D. And you can see how this tectorial membrane, right as I'm tracing out in black here, look at how that's laying on the top of the hair cells. Now, it's very important to realize, okay, remember, this is all endolymph here. Endolymph surrounds the hairs, whereas cortilymph is inside of here, okay? It's very important, and here's another picture, to realize that the hairs of the inner hair cells do not touch the tectorial membrane. Only the hairs of the outers do. That's why this picture here is outdated. Look at this. It's showing you as if the hairs are touching. That's before we knew better. This picture is probably 40 years old, okay? And I show this to you to give you a bit of an idea of the evolution of our field. We have learned that inner hair cells are shaped different than outer hair cells. Look at the different shapes. They're showing you like they're the same. Okay, you can tell this is an old picture. It's before they knew what the differences were. They just knew, oh, we had one row of inner hair cells and you had several rows of outer hair cells. But they didn't know why and didn't know what they did. So now, looking here, you can see that the inner hair cells are fat and the outer hair cells are skinny. And look here, inner hair cells are fat, like pears, and outer hair cells are shaped like test tubes. They're different shapes, and it means they do different things, completely different things. Inner hair cells are afferent. Outer hair cells are efferent. We didn't know that before. We didn't know what they did. All of this stuff is so tiny. Here's a real picture of a real human cochlea, and you can see scala vestibuli, Reissner's membrane, spiral ligament, stria vascularis, basilar membrane, outer hair cells. The tectorial membrane is really small here. It should be going all the way out here, but this person's dead, and so it has shrunk. Okay? Now let's look at this triangle really closely. And here's the hair cells. Here, the tectorial membrane is not shown. Closer. Now look at here. The tectorial membrane's been torn off, and you're looking at inner hair cells and 3 rows of outer hair cells. This is one hair cell. There's another inner hair cell. There's another inner hair cell. So I see kind of 1, 2, 3, 4, 5, 6, 7. Okay. Here's one outer hair cell, another outer hair cell, another outer hair cell. So we're looking down at them from the top. Here's a picture of damaged hair cells. Now, most damage occurs to the outers and less to the inner. What's the significance of that? Inner hair cells send all info to the brain. Without the inner hair cells, you are as deaf as a post. Nada. But the inner hair cells have a fundamental flaw. They can't pick up sounds below 50 dB. They can't. Okay? They need help from the outer hair cells to pick up sounds of 10, 20, 30, 40. So if you've got outer hair cell damage, what do you have? You have an inability to hear sounds below 50. You have a moderate, average degree of hearing loss. You have presbycusis, Presbyterian Church of the Elders, presbycusis, hearing in the elders, trouble hearing treble. And the damage to these hair cells will be confined mostly to the base of the cochlea, where the treble frequencies are represented. And so people with sensory neural loss who've hit 65 and they're having trouble hearing their grandkids, they've got this inside their cochleas. And this damage to the outer hair cells is, again, mostly at the wide base of the cochlea. Here's a picture of hair cells again. Inner hair cells on the top, outer hair cells shown from the top, but now you can start to see the test tube shapes underneath. Here's that you can see how they're pilloried. The hairs are completely separate from the cell bodies, totally. And again, endolymph surrounding the hairs, cortolymph surrounding the cell bodies. They are completely cut off. They're pilloried at the neck. The left is looking at it from the top, and here from the side, you're looking at it from a different angle, so you can see both above and below where the hairs are cut off from the cell bodies. Here's the top of one inner hair cell. The top of one inner hair cell. So how many of these hair cells do you have in each cochlea? 3,000 inner hair cells. How many do you have of outer hair cells? 12,000. Here you're showing 3, so you'd think you'd have 9,000, but please remember, as you go toward the apex, you've got 4 and then 5 rows of outer hair cells. So 12,000 outers, 3,000 inners, for a total of 15,000 hair cells in each cochlea. And on top of each inner hair cell, you have about 50 hairs. And on top of each outer hair cell, you have about 100 hairs. These are things you need to know in your good old anatomy. And the sizes of hair cells relative to a hair on a head, quite small. So I've drawn a human hair here, and now you can see a hair cell on top of the hair. Actually, I didn't draw this at all. Someone named Mead Killian drew this. Now, Killian is a big figure in our field. He lives in Chicago, Illinois, and he is an inventor of a certain type of hearing aid in the 1990s, which tried to imitate the role of the outer hair cells, by the way, by amplifying soft sounds, especially sounds below 50 dB, in order to imitate the outer hair cells electronically. His hearing aid was called the K-amp. And a lot of people are still using a similar type of amplification strategy in our digital hearing aids today. They call it wide dynamic range compression, WDRC, an electronic way of imitating what the outer hair cells do. And we'll talk more about that next week and the week after, because next week we delve into the physiology of the cochlea. We go into Unit 6. And we really delve more into physiology of the cochlea for the next couple of weeks, how it works. But I'm just kind of giving you a little bit of a heads up. Anyway, look at the size of this. You got a human hair, and then you have a hair cell compared to a human hair, and then don't forget you got about 50 to 100 hairs on top of the hair cell. Looking at this, my picture of my buddy the bug, look closely here. It's got a gear in its hand. It's blown up under an electron microscope. Look at the gear closely. As we bring it closer, you'll see a little white dot on one of the teeth of the gear. And as you bring it closer, there's a hair cell. And there's 100 hairs here, but the hair cell is dead, so they're all clumped together. Pretty small, okay? This is an ugly picture. So this one's better. So it's showing you a rolled up cochlea and showing you that high frequencies are located at the base and low frequencies are located toward the apex. This picture is showing you the same thing, and the word is tonotopic. It means specific frequencies are represented in specific places, just like keys on a piano. Okay? Tonotopic. The middle ear isn't tonotopic, the outer ear isn't tonotopic, but the inner ear is tonotopic. Specific frequencies represented in specific places. Here's an actual picture of the spiral ganglion, okay, of a spiral ganglion. And it's showing you eighth nerve fibers, and now look at all the cell bodies of the eighth nerve fibers located here. Spiral ganglion. And if I can just kind of, once again, just make sure we keep our orientation here. Spiral ganglion. It would be showing you one of these guys. Showing you one of these guys. Showing you one of these. Okay, that's all that was. Just keep it. Let's go to our notes now and make sure we're following diligently here. Electron microscopy of normal versus damaged hair cells. We saw that. Hair cells, HCs, consist of cell body and stereocilia on top. Those are the hairs. Inner hair cells, the stereocilia are arranged all in a straight line. Outer hair cells, the stereocilia are arranged in a horseshoe pattern, with the tallest ones toward the back. IHCs and OHCs look very different from each other, and that makes sense because they do vastly different things. Next, more on that in physiology next week. Inner hair cells are shaped like jugs, 3,000 of them, all in one row, all the way up from the base to the apex. 50 stereocilia on top of each inner hair cell. The tips of the stereocilia are not embedded in the tectorial membrane. These are the inner hair cells, recall. The outers are shaped like test tubes. 12,000 of them in each cochlea, in 3 rows at the base to 5 rows at the apex. About 100 stereocilia on top of each outer hair cell. And the tips of the stereocilia are embedded in the tectorial membrane. We will talk more about that next week. We'll show you more pictures of it and the significance thereof. The cochlea is tonotopic. Now, Helmholtz, it was the person who discovered that the cochlea was tonotopic. He's the one who found out that, okay, highs are located at the base, lows are located at the apex. So he's the father of the place theory. In other words, specific frequencies are located in specific places. There was another person named Rutherford. And Rutherford said, yeah, but you know what? It's not just that. I mean, it's the firing pattern of the 8th nerve that tells the frequency. So if you have a 200 hertz tone, that means the 8th nerve is firing 200 times a second. If you have a 300 hertz tone, the 8th nerve is firing 300 times a second. That was his belief. And you think to yourself, yeah, but nerves can only fire 500 times a second. So how do you tell 1,000 hertz? And he would go, oh, 1/8 nerve fires twice a second, and the other one's firing 500 times a second, so 2 times 5 is 1,000. So you get what they call this volley theory. Rutherford's theory is not as popular as the place theory. But Rutherford's theory does explain a couple of interesting things, and we'll look at these in psychoacoustics later on. One of them, though, I'll tell you, is the revving of a motorbike. Ring, ring. How come when you rev a motorbike, your pitch goes up? That's Rutherford's temporal theory. Each is identical white noise. Transient bursts of noise from the pistons of the motorbike, but making them, you go up in pitch. And it's kind of like, oh, maybe that is what the 8th nerve firing. So it could be that both of these theories are kind of working together, but anyway, that's kind of gets a little esoteric. So now let's get back to sharing screen, and let's look at the bottom of page 3. Hair cells and afferent, efferent pathways. Because you've got afferent brain going and efferent back to hair cell from brain. 8th nerve is a bundle of sensory afferent nerve fibers. And you saw that explicitly drawn when we looked at this slide way up here. And it's a rather good slide. I quite like this one. Look at the bundle of fibers, much like a rope. Okay, that's what nerves are. They're not a single strand. They're like a rope made of thousands of fibers all wrapped around each other. Okay, back to your notes. It's a bundle of sensory afferent nerve fibers. As such, it is mainly in cahoots with the inner hair cells. Recall its cell bodies are located in the spiral ganglion of the cochlea. On the other hand, the olivocochlear bundle. Now, what do you think that might mean? The cell bodies are located in the superior olives of the brainstem that we looked at in 110 this morning. And these nerves go in the opposite direction. They're going from the brainstem to the ears. And these are efferent fibers. And where do they terminate? On the outer hair cells. So most 8th nerve fibers terminate on the inner hair cells, and most olivocochlear bundle fibers terminate on the outer hair cells. And the cell bodies of the olivocochlear bundle nerve fibers are located in the superior olives of the brainstem. And let's kind of look at a picture here to give us a bit of a better idea of what that might look like. So we'll go here and here. Okay, follow my cursor. Eighth nerve fibers going here. Olivocochlear bundle fibers going here. Okay, so messages going this way and messages going this way. The cochlea, as they would say in Deutsch, es ist nicht in Einbahnstraße. This is not a one-way street. The cochlea is a two-way street. The nerve fibers of the olivocochlear bundle, however, are far fewer. How many nerve fibers do you have in the eighth nerve? 30,000. 10 go to each inner hair cell. 3,000 times 10 is 30,000. Okay? And if you look at a neural pattern, let's just look at this. Here. Think of here's a spiral ganglion. And you've got, look at how they are afferent. Look at the arrows going away from the cochlea. These are hair cells. They're showing you 3 rows of outer hair cells, 1 row of inner hair cells. Okay? And look at how you've got 10 eighth nerve fibers terminating on 1 hair cell. So these guys are spoiled rotten. And maybe you might have a little bit of an eighth nerve fiber, and it's going to be 1 fiber, and it's talking to about 10 outer hair cells, and that's sending info to the brain. So the outer hair cells are barely afferent at all. The outer hair cells have hardly any afferent sending information. Looking at the slide, you can see again 10 eighth nerve fibers talking to each inner hair cell, whereas you might have 1 eighth nerve fiber and it's talking to 10 outer hair cells. So really, if you turn it the other way around now, and we look at our notes, you can just say that the olivocochlear bundle works exactly the opposite. It's going to send all kinds of fibers to the outer hair cells, and it's barely going to talk to the inner hair cells at all. And that's the message I want to take home. So if we're looking at the end or page 4 now, this is as far as we go in anatomy of the inner ear. Efferent olivocochlear bundle messages course in the opposite direction to those of the afferent eighth nerve. The cell bodies of the olivocochlear bundle nerve are located in the low brainstem, superior olives. Inner hair cells are afferent. They send info to the brain, from the cochlea to the brain. They comprise 20% of all hair cell population, but they get 95% of the eighth nerve fibers. Each inner hair cell gets several, I'd cross out several and say 10 eighth nerve fibers that synapse directly on the inner hair cell. And several inner hair cells share a single efferent olivocochlear bundle fiber. So that's what I mean by the opposite. Outer hair cells are efferent. They send sound info from the brain back to the cochlea. Outer hair cells comprise 80% of all hair cell population, but they get only 5% of eighth nerve fibers. Each outer hair cell gets several olivocochlear bundle efferent fibers that synapse directly on the outer hair cell, and several outer hair cells have to share a single afferent eighth nerve fiber. So basically, in summary, afferent and efferent innervation patterns are generally the opposite. I will say this too. How many eighth nerve fibers do you have? 30,000. How many olivocochlear bundle fibers do you have? 1,800. 1,800. So really, think about the olivocochlear bundle and the eighth nerve in this following analogy. The eighth nerve you can call an interstate. It's got 3 lanes and it's hauling ass. all the way down the eastern seaboard. Okay, just boogieing. The olivocochlear bundle goes parallel to that interstate, but it's like a little country bumpkin gravel road. Okay, because the eighth nerve is way bigger than the olivocochlear bundle. They run along right with each other. They're going in opposite directions, but the eighth nerve has by far the most fibers. But just remember, the innervation patterns are generally the opposite. The eighth nerve is mainly in cahoots with the inner hair cells. The olivocochlear bundle is mainly in cahoots with the outer hair cells. So basically, in a nutshell, that completes the anatomy of the cochlea. We finished this unit, which is great. But I think we've done it better this year than we did last year. I'm thinking I'm figuring out how to summarize things. But first of all, Karen, do you have any questions, anything that's blurry or vague or that you'd like me to explain in any of this? I mean, we're good here. We're only quarter after. So, but let me know do you have any thoughts here?
I think I'm okay.
Good. Okay. Probably as soon as the Zoom session ends, you'll be going, oh my God, why didn't I ask him this or that? No big deal. But we have covered, I think in our notes, I'm going to just lay out what I think people need to make sure that they understand, okay? So I'm going to go to the top of the notes here. Oh, by the way, this picture here at the very end, look at this. This is a hair cell count from someone who did a lot of hunting, who had a lot of noise. Here's this audiogram. Normal hearing, normal hearing, normal hearing, and then boom, down in the high frequencies. And when they looked at his hair cells, they unrolled his cochlea, and they found all kinds of dead hair cells near the base of the cochlea. Whereas toward the middle and the apex of the cochlea, the hair cells were living. Inner hair cells, outer hair cells. He was a right-handed hunter. Now, when you're shooting a rifle, I guess, if I'm right-handed, my left ear is going to be closest to the loud part of the rifle, whereas it's the opposite if I'm left-handed. So when you look at this person, what happened to him? A right-handed hunter, okay? Hair cell damage to the inner hair cells, hair cell damage to the inner hair cells, hair cell damage to the outers. Hair cell damage to the outers. Notice how his left ear has by far the worst hair cell damage when this person died, okay? And that's what it took, just kind of a person who was a hunter, a right-handed person. So it's kind of interesting. Have a read of that. Anyway, that's just for your own interest. In the notes, as we work our way from the top, this section is very important. The vestibular system, make sure you have the fact of human balance comprised of 3 parts, and then the vestibular system itself comprised of 3 parts. And notice how the semicircular canals themselves have 3. There's a real 3, 3, and 3 here. Orthogonal, be sure you know what that is. Don't worry too much about the ear stones and all of that. Ampullae, maculae, utricle. You should know what utricle and saccule are. Know what the word nystagmus means. That's the following tracking of the eyes. And know what BPV is. ENG. Know what these are. Okay? And then the gross anatomy. Be sure to know that the cochlea has 2.5 turns, not 3.5. Don't worry so much about ductus reunions. And don't think that you have to memorize perilymph being high in one of these than the other, because if I had to tell you that, I probably would have to look in my notes. Okay? Just know that perilymph and endolymph are opposite in chemical composition. That's what you need to know. Don't worry about the Na and the K. Know the scala vestibuli, of course, scala tympani, scala media, helicotrema, obviously. And of course, know these pieces and parts too. Reissner's, basilar, spiral ligament, stria vascularis, modiolus, spiral lamina, spiral ganglia. And then know what the organ of Corti is, of course. Concentrate on knowing that the basilar membrane, mass and stiffness properties. Tectorial membrane touches the top of the outer hair cells, not the top of the inner hair cells. Don't worry about knowing the names of the supporting cells. That's not what I'm interested in. Know what cortolymph is. Don't worry about the Na and the K, but know that it is actually like perilymph, but inside the scala media. Outer hair cells versus inner hair cells, yes, know the numbers and know the numbers of the hairs. Know what the word tonotopic is. Associate the name Helmholtz with tonotopic. And then have a passing awareness in finality regarding the eighth nerve versus the olivocochlear bundle. One's afferent, one's efferent. One communicates with inner hair cells mostly, one communicates with outer hair cells mostly. That there would be done. Hey, hey. Hey, hey. Okay, good stuff. I will stop recording here and upload this puppy as a YouTube video. I've already done the acoustics one from this morning. I've been working at that quicker because I have to head up the mountain and go to some crazy presentation later this afternoon. Okay, live long and prosper. Adios. It's been a slice.